So this is a practical guide which is related to the A levels chemistry experiments, all the practicals. The safety and the hazard. First, how or what is the difference between the hazard and a risk? So hazard is actually like a substance is there which has a potential to cause an harm, and risk is there like it's a chance that the hazard will cause a harm. Like there's a chance, and risk is there. For example, if we say a substance is toxic. So when we say a substance is toxic, so this is a hazard. A substance is corrosive. That is a hazard. A substance is flammable. Hazard. A substance is oxidizing. Hazard. So how we can minimize the it has a potential to cause an harm. It can harm us, or a substance is harmful to the environment. And how we can reduce risk is there. Like if a substance is toxic, it will be toxic. If a substance is corrosive, it will be corrosive. But what we can do, we can minimize the risk. How we can minimize like the potential, like it will cause the, because risk is the chance that the hazard will cause harm. So how we can limit that, how we can minimize by using small concentrations, by using a test tube reactions, by wearing gloves, wearing goggles, using lab coats, using the conditions which minimize the hazard, minimize the risk, I mean, not hazard. So that is the main difference. Hazard is like it's about the danger of a substance, you can say. So hazard cannot be changed. Like if acid is corrosive, it will be corrosive. You can, but what you can do, there's a risk when you will use an acid. The chance is there that it will cause an harm. So you can minimize the risk. Is it clear? The difference between the risk and a hazard? So as you can see here, these are the hazards. If a substance is irritant, it is a hazard. Like usually like dilute acids and alkalis. And how we can minimize the risk when we are wearing the goggles. Corrosive, if a substance is corrosive, like strong acids and alkalis are corrosive. So how we can minimize the risk when we like, because it will cause a harm. So we wear goggles. Flammable substance, it will be flammable. So that is a hazard. But how you minimize that, you don't expose directly to the flame. If a substance is toxic, it will be toxic. So you wear gloves, avoid skin contact, or you wash hand. That is, you minimize the risk. So it will not cause harm to you. Then measuring a volume. When we are measuring a volume, for that purpose, we use a gas syringe whenever we want to measure a volume. Variety of apparatus could be used, but specifically if we want to measure the volume, a gas volume, we use a gas syringe. So a gas syringe can be used for a variety of experiment where the volume of gas is measured, and a possible to work out moles of a gas and follow the reaction rate. We can work out that. What are the potential errors when you are using a gas syringe? The gas might escape before a bung is inserted. Like when you place a bung here, maybe the gas might escape. The syringe sticks. Like what does it mean? Maybe the gas is released, but the gas pressure is not enough to push the gas syringe, like increases the volume. So that is one possibility. And some gases like carbon dioxide, sulfur dioxide, they are soluble in water. So when a reaction happen or occur, maybe that gas is not completely released outside. That some of the gas might remain dissolved. So if some of the gas might remain dissolved, that will not give you the right amount. For those who just joined the session now, this is the today's session is totally related to discussion of the experimental technique, the experimental process which related to the practical chemistry. Follow rate means like we can measure the rate of the reaction. How we can measure the rate of a reaction? Because rate is the change in the volume divided by time interval. So we measure the volume of a gas given off and divided by the time interval, we'll get the rate at which the reaction proceeds. That is what we can do. And what you have to do, you have to make sure you don't leave a gap on your diagram where the gas could escape, as you can see here. And if you draw a gas range, you have to make sure draw it some measurement marking. Like when you're drawing these gas ranges, even in the questions, there should be markings on the gas range. The gas can dissolve in the mixture because if a gas is released, that gas might be dissolved in the mixture. So the true amount of the gas will not be what you recorded. Practically, it might be higher than what you recorded. Like experimental result does not fit with the theoretical explanation. Theory suggests you should get more volume of a gas, but practically it would be less because some of the gas might dissolve in water or solution. Another thing, the volume of a gas depends on the pressure and temperature. So when we are recording the volume, it is important to note the temperature and the pressure of the room as well. Because as we know, the gases, according to a Charles law, volume of a gas is directly proportional to temperature. At higher temperature, we'll get a larger volume of a gas. Same thing, if a variation happened during an experiment, then it will result in a different volume because at high pressure, you will receive a smaller amount of gas. And moles of a gas can be calculated from the gas volume, like how we can work out the moles of the gas. We have the equation. There are two formulas to work out the moles. One is moles equal volume of the gas in decimeter cube divided by 24. That is one. Another formula, PV is equals to nRT, the general gas equation. So if PV is equals to nRT, you can find the moles by taking a ratio between the pressure and like the product of a pressure and volume divided by, so PV divided by RT, what it will give you? It will give you the moles of the gas. So it depends on, because this one is valid when you have like standard conditions are there at 25 degrees centigrade or 298 Kelvin or 1 atm, then you can directly use this formula, volume in dm cube divided by 24. But if the conditions are not standard, like the temperature may not be 25 and the pressure is not 1 atm, in that case, you can use a formula PV equals nRT. There's also another way of working out the volume of a gas. What we can do, we can use the measuring cylinder here, and what will happen, this technique is used to collect the gas over the surface of a water so that we can identify when the gas bubbles are seen, we can identify the reaction is taking place. But once the bubble stop formation or the formation of the bubble stop, it means there's no more gas given off. So if there's no more gas given off, it means the reaction has stopped. So, but this technique cannot be used for gases which are soluble. Like example, sulfur dioxide, carbon dioxide, even chlorine can also dissolve. So it won't be effective when for a soluble gases, the gases which can dissolve in water. No, the density of all these gases are density of a gas when you compare to air. Some gases are having a high density than air, some gases have low density than air. But compared to water, they all have low density. Water is having high density than all the gases. That's why all these gases will move up. Yes, I will share this file even on the group. I'll share this file on the group as well. Just after the session, once we are done, I will share this file with you. Measuring the molar volume of a gas, how we can measure the volume of a gas. There are different ways, techniques are there. Like example, these are core practicals, measuring a molar volume of a gas. So what we did, measure a 30 cm cube of 1 mole per dm cube ethanoic acid and transfer into a conical flask. Which piece of apparatus I can use to transfer 30 cm cube? Is it a pipette, a burette, or a measuring cylinder, an imaging cylinder? What I can use? So I can use burette. I can use, but burette it will take time to transfer. But will be accurate. I can also use a measuring cylinder. It will be quickly. It will transfer, but it won't be accurate. So if you mention burette, the drawback is that it takes time to transfer the liquid. But if you mention measuring cylinder, the drawback is that it won't be accurate. So it depends on what is the purpose. So if you want accurate result, we prefer a burette rather than a measuring cylinder. But if you want to do it faster, then we use the measuring cylinder rather than a burette. Then we attach a conical flask. So how we carry out this experiment? We have a conical flask and we transfer, let's say, 30 cm cube of ethanoic acid. The minimum volume a burette can measure is 0.1 cm cube and maximum it can measure 50 to a least smallest value of zero point 0.1. Where pipettes are in a lab, normally we have a 25 cm cube pipette, but variation is there. Some of the labs we can have 15, but commonly in the lab we have 25 cm cube pipettes. And a pipette is having only one marking. So if you want to measure a fixed volume, we use a pipette. A measuring cylinder can measure normally 100 cm cube cylinders are the most common one with a least count or a smallest value of 1 cm cube. So we attach a conical flask to a gas syringe and then, or we can also collect over the water, this gas which is released, or we can connect a gas syringe here. Then measure the mass of a weighing bottle with approximately 0.05 calcium carbonate and add calcium carbonate into a conical flask and resealing the bung so no gas escape. So what we did, we placed this right now, and what we did, we removed this flask and add calcium carbonate CaCO3 and then instantly place it back again, reseal so we don't allow the gas to escape or minimize the gas to escape. Then measure the volume, the final volume of the gas. What is the total volume of the gas given off? Then reweigh the empty bottle test tube for a step 3 and repeat the experiment several more times and increasing the mass of a calcium carbonate by 0.05 grams each time. Like every time we'll increase mass by 0.05. Like first we use 0.05, then we'll use 1.00, I mean 0.10, then we use 0.15, then we use 0.20, then we use 0.25 and repeat this procedure. Then how we analyze? So from like you can use your results and plot a graph as you're increasing the mass of calcium carbonate, the volume of a carbon dioxide gas given off is increasing. So from your graph, read the volume of a carbon dioxide given off. Do we repeat each mass 2 times and measure the mean volume? You can do that as well, but what actually we are doing, instead of we are repeating for each time, because we are continuously changing the mass. So instead of repeating it, you can also do it like one mass, then second, then third. If you do for each mass twice, then you have to take an average volume there. Then from the graph, read the volume of a carbon dioxide given off with 0.25 gram of calcium carbonate. Then we can work out the moles. Moles equal mass in gram over molar mass. So we got the moles of calcium carbonate. And from moles of calcium carbonate, using a mole ratio, we'll get the moles of a carbon dioxide. And after working out the moles of a carbon dioxide, the volume of a carbon dioxide divided by moles of carbon dioxide, we'll get the molar volume, like how much volume is occupied by 1 mole. because we have the formula that moles equal volume of the gas divided by 24. Or what is this 24 actually? If you see this 24 is a molar volume. Actual formula is moles of a gas is equals to volume of the gas in decimeter cube divided by molar volume. Molar volume means mass of 1 mole. And mass of 1 mole, usually the mass of a molar volume means volume of the 1 mole of a gas. So usually molar volume at room temperature at 298 Kelvin or 1 atm, it is 24. So that's why directly we don't write 24. But right now the experiment is finding the molar volume. So if we need the molar volume, so molar volume is what? Molar volume is the volume of the gas divided by moles. So volume of the gas you will have from your graph, and the mass of a calcium carbonate what we use, you will get the moles from that. So volume of a gas divided by moles of the carbon dioxide will get the molar volume of carbon dioxide. Is it clear? This core experiment one, how to work out the molar volume? Anyone having a doubt or a question in this? You can also use another method. What is method of using a gas syringe to calculate the molar mass of a propanol? Or like this is a word example. If you have like 0.15 grams of a volatile liquid was injected into a sealed gas syringe. So there's a gas, when we say a volatile liquid means a liquid which is having a low boiling point, it can easily vaporize. We call it as a volatile liquid. The gas syringe was placed in an oven at around 70 degrees centigrade and a pressure of about 100,000 Pascal. The volume of 80 cm3 was measured in the gas syringe. What is a molar mass of a volatile liquid? Like you can also do this experiment if you want if you have a volatile liquid. So we simply what we did, we have a gas syringe. We place a volatile liquid in the gas syringe. And then this gas syringe is placed in an oven. When a gas syringe is placed in an oven, the heat energy will evaporate this liquid because it's a volatile, so low boiling point. And as a result, what will happen? We'll have vapors only. Like the liquid will turn into a gas and will have vapors. And at a certain temperature, these vapors will apply a certain pressure. So the volume will also change, and eventually what will happen, the syringe will stop expand, like the volume of a gas or a gas inside the syringe will not expand. It means the outside pressure and inside pressure is balanced. So we can use the formula, the journal gas equation, PV is equals to nRT. So if I need the moles, it will be pressure volume divided by journal gas constant into temperature, where P is the pressure, which is 100,000, V is the volume. We took 80 cm3, but this is all SI units should be used, so we have to convert into meter cube. So we substitute meter cube, R is the journal gas constant, and T is the temperature. So when we simplify, we got the moles, how many moles are there? Okay. And then, because if we need the molar mass, like what is the molar mass of a substance? We have the formula that the moles equal mass in gram divided by molar mass. So moles equal mass in gram divided by molar mass. So if I need the molar mass, it will be mass in gram divided by moles. So what initial mass we use? We use 0.15, so we substitute that and the moles. So when we divide, we got the molar mass of this substance, which is 53.4. But remember, this can only be used for the volatile liquids. When we use the term volatile, it means a liquid with a low boiling point. If the liquids are having a high boiling point, in that case, we cannot use this because otherwise, if the temperature is so high for a liquid, the boiling point, then it will affect the gas syringe itself as it is heated to a very high temperature. Is it clear how we can work out the molar mass and the molar volume? Anyone having a doubt or a question? Look, when I say these are the core experiment, means most of the experiments are modified from these origins. Like anything is there, will have these experiments. One of the factor will always be there. So that's why these are the core experiments. Heating a crucible. Heating a crucible, there are different uses for a crucible in the science lab. What is the crucible used for? It is actually a deep container, and mainly if we want to find the water of crystallization or we want to find change in the mass during a reaction when a substance react, we use a crucible. But the most common one in the lab whenever we use is usually finding the water of crystallization. How it is done? The water of crystallization, like example, if you want to find how many moles of water of crystallization are there with calcium sulfate, and these compounds which contain a water of crystallization, we call them as hydrated compound. So first what we did, we weigh an empty, clean, dry crucible with a lid. Like this is a crucible with a lid. So we use a balance and we measure the mass of this whole apparatus. Then we add 2 grams of a hydrated calcium sulfate. It can be any hydrated compound. In this example, it is calcium sulfate, but it can be any compound. We can use we can use copper sulfate. Hydrated copper sulfate could also be used. Then we heat strongly with the Bunsen burner for a couple of the minutes, and then we allow it to cool. Then we weigh the crucible and the content again. Until what point we will continue, we'll heat the crucible again and reweigh until you reach a constant mass. And that to ensure that the reaction is complete or all of the water is being lost from the substance. That's why we heat to a constant mass. And the purpose of the lid is to improve the accuracy of experiment, like as it prevent the loss of a solid from crucible. Same thing. Usually the lid of the crucible is a bigger size. The lid of the crucible is actually a bit bigger than the opening of the crucible, so that some of the gas can escape. Okay. So normally large amount of hydrated calcium carbonate, like example such as 50 grams, should not be used. Why a large should not be used? Because this experiment, like not to be used in this experiment, as decomposition is likely to be incomplete. So that's why, like example, if I use a 50-gram, greater percentage will be there, greater mass will be there, which will not decompose because it need a very high temperature. So that's why we use a smaller proportion of a substance. And the crucible need to be dry, otherwise a wet crucible would give an inaccurate result. So it will cause a mass loss to be too large, because let's say you use a crucible which was moist, some water vapors were there already. So and you place a calcium sulfate, 2 grams of a calcium sulfate, and you supply the heat energy. So when you supply the heat energy, not only the calcium sulfate loses its water, but this water will also be lost. So as a result, it appeared that the greater mass of the content is being lost. So, and a small amount of a solid such as 0.1 gram should not be used. Why 0.1 should not be used for this? As a percentage uncertainty in weighing will be too high. What is a percentage uncertainty? For those who are taking physics, like the percentage uncertainty is the uncertainty in the measurement divided by value recorded into 100. That is the percentage uncertainty. Uncertainty depends on the type of instrument we use as well as the technique. But the value recorded, because if I record a very small value, then I will have a higher percentage uncertainty. So we cannot use a very large mass. We cannot use a very like small point 0.1, point 0.2. So it should be a moderate 2 grams, 3 grams is practically enough for carrying out this procedure. So example, 3.51 grams of a hydrated zinc sulfate. This is also like an experiment, like how it is done practically. So let's say 3.51 grams of a hydrated zinc sulfate was heated and 1.97 grams of a zinc sulfate were obtained. Use this data to calculate the integer x. So how we can calculate? If we want to find what it's a mass of a hydrated zinc sulfate and this is a mass of anhydrous zinc sulfate. So when we take a difference, we'll know what mass of a water is there, 1.54. So mass of anhydrous 1.97, mass of water 1.54. Then we divide by the molar mass which of zinc sulfate here. So we got 0.0122 and 0.085. Then we divide by the smallest value in the combination. We got 1 here and 7. So it means that this formula, like it contains 7 moles of a water of crystallization. So ZnSO4 dot 7H2O will be the right formula for this. Is it clear how we worked out the moles of water of crystallization? Anyone having a doubt in this? So calcium sulfate, can I know the ratio from equation? Yes, you can also know calcium sulfate. You can also know this is zinc sulfate is done. Same thing you can do for calcium sulfate after knowing the mass of the uncertainty. Remember, the uncertainty is a percentage uncertainty is the uncertainty divided by value recorded into 100. So if you use a very small mass here, so small mass means we record a small value. If we record a small value, then the percentage uncertainty will be very high. So that's why we should not use a very small mass of a substance. And why not very large? Even if we use a very large, we'll have a very low uncertainty, percentage uncertainty, I mean. But the problem is that practically it is not correct. Why? Because practically 50 grams of a substance will not decompose when you supply heat energy. It's a too large mass because when you look, when you're using a 2 gram, so most of the substance will be in contact with the crucible. But when I use a 50 gram, the substance will be like this. So this particle here is not direct in contact with the heat source or not in contact with the crucible. That's why it will take time to transfer heat energy. As a result, maybe the water of the crystallization which are present here may not be lost. That's why we are not using a very large mass. Would we have to write these experiments? No, not full experiments you have to write. Not the full experiment. You have to write. It's like the experimental techniques are there. This is how you carry out. So sometimes they ask like, what should be done? Till what point we should heat the crucible? Like these type of questions are there. For a ratio, it's 1 is to x or it's 1 plus x. No, for the ratio, when you're taking a ratio, it's a hydrated. Actually, it's a ratio between anhydrous salt and water. That is the mass you're taking. How to get the mass of anhydrous? Like you first you measure the mass of hydrated salt. You would took 2 gram. When you supply the heat energy, you will get the mass of anhydrous. Let's say it is 1.8. What is the mass of the water? So 2 minus 1.8. So mass of a water is 0.2. And mass of hydrated salt is 1.8. Because that's the water crystallization being lost. Then what you do, you divide by the molar mass, like their water molar mass is 18 and the salt molar mass according to salt. And then you divide by the smallest value and that you will get the simplest ratio between them. Is it clear? No, hydrated salt, we don't consider this as 1 mole. It's not about one or X. It's not like this. The height, what you will have, because you're doing an experiment. So you first you will place the crucible. You already know that you are taking 2 grams. So that is the mass of a hydrated. Then you heat to constant mass and you will get the mass of anhydrous. How you get the mass of anhydrous? Because you already, in the beginning of experiment, you measure the mass of empty crucible with the lid. So you measure the mass of empty crucible with the lid, and let's say this was 2 gram. And you measure the mass of a crucible and the anhydrous salt together. Let's say it is 3.1. So this is anhydrous, means after heating. So you take a difference of the masses, you got 1.1 gram. So this 1.1 gram is a mass of anhydrous salt. And how to know how much water is there? You have the hydrated salt 2, you have anhydrous 1. So you subtract the two masses to know how much water is used. So 0.9 grams of a water mass is there. So you will take a ratio between the mass of, first you will compare the mass of anhydrous salt with the amount of the water which is present. And then first find the moles of each and then find the mole ratio. So it's actually finding, the main thing is you should know what mass of anhydrous salt you have and what is the mass of a water which is released. Then find the moles of each and then take the mole ratio. And what answer, the final answer you get, that will be the ratio, like exam, because whenever you're taking a ratio, this will be the smaller number. So this will always be 1. So it is 1 ratio X here. But this is what you're taking a anhydrous and the water. So anhydrous was, the mass of anhydrous was 1.97 and the water was 1.54. These are the grams. When you simplify, like you divide by the molar mass, then when you got the answer, you got 1 is to 7. It means the ratio of anhydrous salt to water is 1 is to 7. So if the ratio, so what is the formula of hydrated salt?